I'm thinking about compilers, which I'm sure is a much more exciting topic. Probably not. We have an assignment due Wednesday. We have a review session scheduled for Thursday. We have an exam scheduled for Friday. Pretty typical week. Any questions before diving back into content? I guess I can paint the remaining schedule. We're down to 2 weeks plus finals left to go. So with 2 weeks plus finals, we have a couple of assignments. We have the project that I'm going to be assigning basically as soon as I can go over LL parsing, which may in fact be today. I'm thinking we'll probably get far enough to reveal the project today, which would give you at least a couple weeks to work on it. So getting started with the project, assignment this Wednesday, assignment next Wednesday, project due sometime over finals week. And then third exam Friday, final exam over finals week. It's a bit of a rough end to the quarter, but that's the quarter system. All right, last time we talked about first and follow functions. And we basically got through them both. So we were on this last example follow function, but I think we rushed through it just a little bit. So I think there was one prior slide to this that did follow F and follow A for this grammar. Were there any questions on follow or the result that we got? I'll actually just go back and do it one last time. Just to remind you of that process. All right, so follow is getting at when you have a following non-terminal, you're looking for every possible terminal that could be the next terminal in a derivation that comes after the expansion of that non-terminal. So follow of S says anywhere an S could appear in the right-hand side of a grammar, what is the set of terminals that could appear after that? So follow of S was the easy one in this case, where we look on the right-hand side, we see an S here, and we see that all we can follow that S is a C. But first, we have to remember that wherever S is in the grammar, that the expansion of S can create the end of string marker. So follow of S has the end of string marker $, and then from here we have a C that can follow that S. Follow of A was a lot more difficult. From here we saw we could follow D from A, so we just add D to follow of A because it can follow the A. Here we had a recursive definition from A, where what comes after this A could be whatever comes after this A, because this A can end this A production. But since it's recursive, what can follow A can follow A. That just says that we're going to add what's already in there. So we don't worry about it in this case. If there were another non-terminal, like if an A ended something else, like this production, then we would have to say whatever could follow S could also follow A. Just because in the derivation of S, we could pick this, which after that A could come whatever could follow the S in the first place. So we don't care about this one. But there is this A that is followed by a non-terminal. Whenever we see two non-terminals in a row like this, whatever can follow A could be in the first of the derivation of S. So we have to add everything that could possibly be in first of S to follow of A. And first of S can be this A or anything that is in first of B. First of B could have been this B, but also it could go to lambda. If it goes to lambda, this B goes away, so we have to look at the first of this A, which could have been C or D. So from all of this, we had A present in first of S. We had B present in first of S. We had C present in first of S because the B could go to lambda and D was already there. So basically we're adding A and B and C to follow of A, because what could follow A is this S non-terminal, and this S non-terminal could derive C or D or B or A from its first. All right, that was everything from follow of A, then we have to do follow of B. We see that D can follow B right there. But also, we have to query first of A, because what could follow the B could be what's in first of A. And first of A is just C and D here. So we already had added D, so we just have to add C to that set. And this becomes the follow set for every non-terminal. And we do a lot of querying for that, but it's okay. In general, you will find for LL and LR parsing, you will be doing a lot of first and follow calculations. Really, it's just LL parsing, but the first step of LL is going to be calculate the first and follow tables, so that those are lookups instead of calculations. Shouldn't have erased that quite yet. Questions? All right, that was follow. All on the slide, necessary. Just like we did for the first function, we can go through a logical sequence of steps to show that our follow function is correct. We just have to show such a derivation exists for everything that we added to our follow function. Again, this does not show that it is complete. It just shows that everything that we added has some derivation. So you will need to do some additional logic to determine whether this is complete and not just correct. So here were all of those derivations. We just go through and show via some expansion starting at the start non-terminal, we can derive everything from following that non-terminal. So here's a derivation that shows a C following an S. Here we have a derivation of, once we get there, we can show that there's an A following an A. So we get that right there. Here it is, a B following an A. Once we get that far out, we get that. Once we're there, we're good. A C following an A. That takes you quite a while to get to, but once we do, there it is. And then we have a D following an A very quickly, follow B. You can't expand. There's the C following a B. There's the D following a B. And again, that just shows that there exists for everything that you identified in your follow at least one derivation that puts it there. That said, if there's something missing, if follow of B could have contained A or B, we wouldn't ever have queried it because we didn't add it to our set in the first place. So make sure that you're also thinking through what you didn't put there. Questions before we move on to LL parsing? Kind of wrapping this self-contained process into a larger process that we can use to actually parse. All right, let's go do it. We're getting so close. This is the second to last slide deck that I have prepared. This actually means we will probably run out of material this week, which also means that I can spend some time next week lecturing on some areas of your interest. Or we could spend some time having kind of extended office hours and give you a chance to work on homework or projects, something that can allow you to not have to do that at home and have some help at the same time. So we're almost there. All right, we know what the first and follow functions are now, so we can now use them to parse efficiently. We thought CYK was efficient. I don't know if we ever thought CYK was efficient, but now we can really get an efficient parser, which is great. To do this, we're going to be converting our context-free grammar into an NPDA. We had some experience with this before. We were using Greibach normal form to do this. We converted the CFG into an NPDA, but there's going to be a separate process that we can use that mimics LL parsing as well. We can actually see how it works. So let's see a second way of converting a context-free grammar into an NPDA. Every one of these is going to have 3 states. We're going to have an initial state Q0. The entire purpose of Q0 is a single transition out of Q0 that pushes our start non-terminal on the stack. So what goes on the stack are just non-terminals. The terminals are going to be when we read past elements in the string. So the non-terminals are our expansions. Our terminals allow us to read past things in the string. So Q1 will be all of the parsing, and Q2 is just a final state that we get to on an empty stack. When we can remove the start non-terminal, when we've evaluated the start non-terminal into its components and have removed it to the point where there's nothing left on the stack. So Q0 to Q1 pushes the start non-terminal on the stack. There's our transition to do so. So now, instead of having A's and B's like we have before, our stack alphabet is just the non-terminals in the grammar. Our middle state, Q1, needs to be able to replace every left-hand side with a right-hand side of each production. And for each of those rules, where we have non-terminal arrow, some sequence of terminals and non-terminals, we're going to add a transition in that where we can pop the non-terminal and replace it with the sequence of terminals and non-terminals that we see in the right-hand side of that production. We need to match the symbols that we see in the input with the order they appear on the stack. So as we are pushing these terminals and non-terminals onto the stack, we're going to be looking for, if there's a terminal there, it needs to be the terminal that we're going to match to our input string. If there's a non-terminal, we need to be able to derive some set of productions that allow us to reach that terminal that is the next terminal that we need to read. And it turns out that there's a simple table that we can make that will allow us to be able to do that. But to do that, we're going to need that first and follow. So for every terminal symbol, we're going to add transitions to Q1 that move past that symbol in the input. So from Q1, if we read the symbol T from the string, we can pop the symbol T from the stack and replace it with nothing. This is just a pop transition. Move past T in the input string, pop T from the stack. If there's a non-terminal on the stack, on the other hand, that's where the fun happens. We already had that, though, replacing each left-hand side with a right-hand side. So we can do that for every possible right-hand side for that non-terminal. But that's it. Those are the 2 different kinds of transitions that we see in Q1. For Q2, we can only go from Q1 to Q2 if there are no more characters to read in the input and the stack is empty, aside from the bottom of stack character. So there's that transition. So we have a multi-push transition on a non-terminal, replacing it with a legal right-hand side. And we have a pop transition that gets rid of a terminal. Any questions on any of these steps or this process? How this mimics? What we're going to need to do? move into an example. Once I see pens stopping scribbling, I will do that, making sure you have a chance to catch up. Let's get into it. Here's a grammar. We're going to create an NPDA that models the LL parsing process for this. So we start at Q0 and push S onto the stack. There's our transition for that. We then need a transition rule for each production. What are those going to look like? What kinds of them do we have? Let's draw it out. So if we're drawing this as an image, we would have Q0, our initial state. We're going to transition to Q1. We're going to do this when we read nothing. We're going to pop our bottom of stack character. We're going to push on the bottom of stack character. So that involves no read from the string. This is just something we do to set the process up. We then get to Q1, where all the fun happens. So we're going to break down our transitions into two major types. There are the types that read past each possible terminal character, and those that replace all left-hand sides with right-hand sides. So we need to be able to read past an A and a B. This is just the string language here. It's just A and B. So we need to be able to read an A, pop an A, push nothing, read a B, pop a B, push nothing. Then we also need to be able to read each and replace. These are going to involve no string reads. So there's no input read for any of these. So each of them we're going to start with, we're moving past no character in the string, but we're going to pop an associated left-hand side and replace it with a right-hand side. So we should be able to pop an S and push an A in its place. That is this transition here. We need to be able to read nothing, pop an S, push the ASB. We need to be able to pop nothing, or not, sorry, read nothing, pop an A, push a lowercase c in its place, read nothing, pop an A, push a B, capital A, lowercase a in its place. So two different kinds of transitions. And as we do that, we should be able to eventually reach the bottom of stack character, and we should be able to read nothing, pop bottom of stack, push bottom of stack, get to a final state that is Q2 that we can accept from.
So the transitions, the A lambda, the B lambda, those are just so we don't have the terminals on the stack once we're done.
Yeah, this allows us to read past them in the string.
So what about C? Do we need one for C?
I guess, yeah, we do need one for C. For some reason, it was B, A, there is a C. You're absolutely right. There is one more. C, C. Yeah. Good catch. So it's an example of a string that's in this language that isn't a single character long. C is in this language, but it's not the example I want to use.
A, C, B, right?
Yeah, ACB. So if we're looking at the stack as we do this, we should, I'm just going to draw them as a sequence of things here. We're going to throw on the bottom of the stack character as we do this. We move from Q0 to Q1. From Q1, at this point, we still have the ACB to read. We haven't read anything in this string. We can manipulate this S in some capacity to get there. What should we do? Should we replace the S with the A or the S with the ASB in order to get ACB?
ASB.
We want the ASB. Note that there's no way for us to know that right now. This is what's going to come with the rest of the LL process, is we'll be able to determine exactly which one of these to do. Right now it's non-deterministic and it requires our intelligence to tell it which. Eventually there will be no non-determinism. We will not have to guess. So the next phase of this is to replace that S with an AS, right to left, not left to right. ASB. So that was using this transition, and again, we read past no input character when we did that. Now the top of stack character is an A, so we can use this transition to move past it. So we're going to get rid of this A on the stack as we move past this character on the string. With this S remaining, we can now do the S arrow A. And that eventually becomes the C via the A to C transition. So this is the S to A transition and the A to C transition. As you do that, your C is the top of stack character. So we can now do this transition that removes the C, pops the C, moves past the C in the string, and then uses the B. We can use that transition, pop the B, move past the B in the input, and what's left is the bottom of stack character. We're at the end of the string, so we know it's time to transition to the final state. Stack is empty. We're past everything in the string. We're in a final state, so we can accept saying that that string was in the language. Any questions on the process? Why these transition rules work in this case? Okay. So that's the setup for how to use an NPDA in a way that mimics the LL parsing process. The real difficulty is removing the ambiguity. And what will be useful as we do this is to be able to see exactly what this process looks like when it's drawn out. So let's go ahead and do this for the ABCAB. We did it for ACB, but let's try to do this for ABCAB and do it in a similar way where what you're going to want to draw is the contents of the stack, the state that we're in, and the current look-ahead character. What is the character that we are trying to put on the top of the stack so that we can move past it in the input? So as an example, the first one that you would start with is just a small stack, just the Z. We're in state Q0, and the look-ahead is the first character of our string A. So you'll just draw this out as a sequence of what's the next stack after the next transition, what state are we in, what's the look ahead. So we have our stack, we have our state, We have our look ahead.
What is the look ahead again?
It's the next character that we want to read in the input. So right now it's the A because it's the first character there, but once we've moved past that A, the look ahead is going to be this next character, the B, and then the next character, the C.
Once we pop the A.
Yeah,
Okay,
yeah. Once you pop the A from the stack and move past it in the string, it's the next character that we are looking for. You think we get there? So let me check your work. We can see from the first second here that we moved from Q0 to Q1, pushing on the S. It's the only thing that changed. Our look ahead is the same. This S became ASB. As that happened, our look ahead is still the A, but we see that this now matches with the look ahead. So we can pop that off, moving the look ahead from an A to a B as we get rid of pop the A from the stack. Always in Q1 for now and forever until we're done. This S now gets replaced with an A. This S gets replaced with a BAA, the two different possibilities for productions that use the S and then the A. We get the BAA there. This now maps the B with the look ahead that we want, so we can pop the B off, move past it in the string. We're to the first C. This A that's now on top of the stack can directly become the C that we then pop off. What's left is the A, which is the next look ahead. We can pop that off. Next look ahead is the B, we can pop that off, and then we get to the end of string marker as the last look ahead. So we can transition freely from Q1 to Q2, and except because we know we're at the end of the string, because the look ahead is $, we're in a final state, and the stack is empty. Questions? Any clarifications or confusions, or someone who got something different and wants to know why? Okay, we'll see if I have time for this. I have to stop partway through. So, if we store all of this information as we go, we can combine the NPDA with the concept of the look ahead. And based on the information that we're going to store in what we're going to call the LL1 parse table, we can determine what to do when there are multiple options. So if we look back at here, wherever there is a non-terminal on top of the stack, there were multiple options about what to do. We could have replaced in step 2 the S with either ASB or A. How do we know which one to do? Likewise, in steps 4 and 5 and 7, there were multiple options about how to proceed. So for the LL1 parse table, the rows of it are going to be all of the non-terminals in the grammar. So S and A and B in the last grammar. And the columns are all of the terminals of the grammar as well as the end of string marker $. So it's going to look something like this. How we're going to fill this out, though, is to basically say, what production do we use when the left-hand side is the row and the look ahead is the column? Which production do we apply if we want to go from the non-terminal to this terminal? Does that make sense? When we have an S on top of the stack and we want to produce, the look ahead says an A, which production should we apply? So to fill out this table, we're going to need to refer to the first and follow, which is why we made them in the first place. So we're going to come back tomorrow and do that. We're going to, for the grammar that we just looked at, calculate the first and follow, fill out this table, and then be able to show that there is no remaining ambiguity with regards to which production we should apply when we have that pair of non-terminal on top of the stack, terminal that is to look at. I will see you tomorrow for that. Office hours starting now.